This presentation will describe a novel flow control mechanism to avoid multi-point progressive blocking in hard real-time priority preemptive networks on chip. I am Leandro Indrusiak from the Real-Time Systems Group at the University of York, and in this paper I worked together with Alan Burns, Nikolai Smirnov, and James Harris. This presentation will cover the basics of priority preemptive wormhole networks, including their real-time analysis and also the recently discovered multi-point progressive blocking problem, referred to as MPB. We then present the proposed router architecture that tries to avoid the problem of MPB. We evaluate this router architecture with regards to its impact on schedulability, also the potential of customizing the widening of the local link of the router, and also the implementation overheads with an FPGA prototype. And I'll close the presentation with some conclusions and future work. Wormhole networks have been studied over the past 3 decades, and more recently they were widely used in on-chip interconnects for multi- and many-core systems. In a wormhole network, packets are forwarded fleet by fleet, so routers don't have to buffer the entire packet. This is attractive for on-chip networks because of the low area overhead and the low energy dissipation that results. The router is actually implemented as a set of input ports which are buffered and a set of output ports connected to those inputs through a crossbar switch. And this crossbar switch is the connection between input ports and output ports is controlled by arbitration control logic. If we implement multiple virtual channels by allowing separate input FIFO buffers for each priority level at each input port, we are able to calculate upper bounds for packet latency in wormhole networks on chip, as long as the output ports follow a priority preemptive arbitration that will always send out at every cycle a fleet from the input ports routed to that output that have the highest priority and that have available buffer space downstream. Several schedulability tests were derived for such a network architecture, and the most cited of them was proposed by Alan Burns and Zheng Shi in 2008 at the NOCs conference. It calculates the worst case latency for a flow TI of sporadic packets characterized by the priority of this flow, the period of the flow, the no-load packet latency, and the release jitter. Xiong et al. Have discovered a scenario where the downstream indirect interference forced all previously known schedulability tests to produce optimistic figures. That means Shi and Burns and all other analyses that were derived from it. This scenario was named multi-point progressive blocking. While in another paper, Xiong and al. Have provided a safe analysis, we have also shown that that analysis was unnecessarily pessimistic in our paper from date 2018, and we have improved on it and further improving in a work led by Borislav Nikolic that was published last year at the Real-Time Systems Journal. So those analyses are safe against MPB scenarios, but to account for those effects, they have higher worst case latencies for each and every flow over the network on chip. So to avoid this inflation on the worst case latency of flows over wormhole networks, this paper proposes a new flow control mechanism and a router architecture implementing that flow control mechanism, aiming to avoid completely the MPB problem. If we can avoid that problem, simpler analysis such as the one proposed by Shi and Burns can be safely used, and we can obtain schedulability gains. So our approach is to avoid the back pressure caused by downstream indirect interference, which is what causes MPB, and we will do this by allowing every fleet in an input port that is blocked towards an output port that's already in use, so that they can be ejected to the memory of the local tile. To achieve that, we have to make a few changes over the baseline architecture that I've shown a few slides ago. First, every time a fleet doesn't obtain arbitration to its desired output port, the input ports will send them through the local port, the port that connects the router to the local tile. The network interface that controls the access to the local tile will then be responsible for re-injecting those flits to the original outputs that they desire to go to, they were supposed to be routed to, once those outputs become free. The output port arbitration has to be changed in such a way that it will give priority to flits coming from the network interface over flits of the same packet coming from input ports to prevent flits from being forwarded out of order. And finally, we will need to widen the local link from the router to the network interface and the local tile so that multiple ports can simultaneously eject flits in case they are blocked. Here we have the baseline network in a simplified schematic showing 3 non-local ports, north, west, and east, and 1 local port that sends flits to the local tile where the local core and the local memory subsystem is. Our proposed architecture will require widening of the local links so that multiple flits can be ejected to the local memory simultaneously. Once we have that, all flits that are blocked and are not able to access an output port are instead sent to the local link and don't stay in the input buffers of the input ports. Let's see an example where that happens. Let's assume a packet Q is coming from the east port and it's going out through the north port, flit by flit. Once a new packet arrives over the west port, this packet will request arbitration to the north port, but it will not be given arbitration, so it is blocked. Originally, it will stay in that buffer and will start causing back pressure whenever that buffer is full. In our approach, that flit will instead be ejected to the local tile via the local port. And subsequent flits of that same packet will also be sent to the local tile. And this will keep happening until the packet that was using the output port, the desired output port, finishes. And this is the last flit of packet Q. And at that point, packet P will start sending flits through that output. And at this point, the new arbitration will ensure that flits coming from the local port take precedence over flits coming from a non-local port, both from the same packet, aiming to access the same output port. So P1 will go while P6 will also be ejected to the local tile and then re-injected by the network interface. By this simple set of changes, we are able to completely avoid MPB scenarios. More than that, we can have simpler flow control mechanisms that don't require credit-based mechanisms. This will always result in minimal buffers in the input ports. On the other hand, we need more wires for the widened local link between router and network interface, and we will also have a much higher complexity in the local tile memory management and interfaces, which is a problem that is not necessarily trivial, and there are several issues that were left as future work. Now, let's evaluate this new router architecture. And the first evaluation we do is to see the impact on schedulability. To do that, we compare several approaches on multiple levels of traffic load mapped to 2 different network-on-chip architectures, 5x5 and 10x10 cores. The approaches are the state-of-the-art approach, which uses the NOC baseline router and uses the state-of-the-art MPB-aware analysis by Nikolic et al. At RTSJ 2019. Because the proposed architecture uses widened local links, which effectively gives more bandwidth to the NOC, it is fair to assume that we should compare with a baseline that has that same amount of additional bandwidth. So we call SOTA up as the state-of-the-art analysis with a baseline NOC with an upgraded local link with higher bandwidth. Then we have the SB baseline that uses the baseline network on chip and uses an MPB unaware analysis by Shin-Burns, which is unsafe. And then we use the proposed router, which we call SB up, and it has the same Shin-Burns analysis from NOx 2008, but with our new router, because our router is immune to MPB, this analysis becomes safe. And here we have the results. we can see that using the state-of-the-art analysis and a baseline NoC, there's a hard impact on schedulability. As we increase the number of flows per flow set, as we increase the load over the NoC, we see that schedulability declines fairly quickly. If we have the upgrade on the local link bandwidth, which is the dark blue line, we see that schedulability doesn't fall as dramatically, but still with around 300 flows per flow set, we already passed the 50% schedulable mark, which means that from the 100 flow sets that we have generated, half of them will not be schedulable with that particular configuration. The other two lines show the unsafe SB analysis in red, using the baseline architecture, and then that same analysis made safe by our improved architecture. So we can see that we are significantly better than the state-of-the-art, and we are better than the unsafe analysis because of the increase in bandwidth that we have introduced in our local links. With a 10 by 10 network on chip, we see that this impact is even harder, which means our approach is much better than state-of-the-art, and this is because the larger the NoC, the more likely it is to experience MPB. Now, let's evaluate if we can improve the usage of chip area by only widening the local link if necessary. And these are the different metrics that we'll see. First, we'll check the percentage of routers that do not require any widening, so we can keep a router which is exactly the same as the baseline. While we'll also check the percentage of routers that require full widening, meaning every non-local input port can simultaneously eject leads to the local tile. We also check the average duplication, and we will check for the multiple levels of load which of those are deemed schedulable by Schoenberg's analysis. And here are the results. We can see as the load increases, we will have a significant decrease of the number of routers that require no widening at all, as you can see in the purple line with the circles. The number of routers that require complete widening for each and every non-local input port increases with the load, but not significantly, and never goes beyond 20% of the router. The blue line with the crosses shows the average amount of local link widening. It is a percentage of the total widening that is required, which is one additional set of wires for each input port that requires widening. So we can see the line never goes above 50, meaning that on average the routers will never have more than 2 ports requiring simultaneous ejection to avoid MPB. We can see very similar numbers on a 10 by 10 network on chip as well. These results give us the confidence that it's a small proportion of the routers that will require complete widening of the local link, 10 to 20% at most, and in many cases, depending on the load, up to 50% of them can be left exactly as they are in a baseline network. Now we evaluate the implementation overheads. We have an FPGA implementation of the proposed router and an FPGA implementation of the baseline router, and we compare them with regards to number of flip-flops, number of lookup tables in the FPGA fabric. And we customize these designs with regards to the number of virtual channels per input port and the number of non-local ports. So for different points of the 2D mesh, you need more or less local ports. And these are the results. With the increase of the ports or with the increase of the number of virtual channels, we see how our approach increases in terms of flip-flops and lookup tables in the red line, and also the baseline in terms of flip-flops and lookup tables in the blue line. You can see that in terms of flip-flops, both architectures are roughly the same, but ours is much more economic in terms of usage of lookup, mainly because of the simplicity of the flow control mechanism. To conclude, we can say that we proposed a vice versa approach here. We adapted an architecture to the respective analysis, and we found substantial gains in schedulability by avoiding completely the MPB problem. Our first FPGA prototype shows promising savings in hardware overheads, and we have shown that customized local link widening has the potential to further improve hardware efficiency. There are still plenty of issues to address. The network interface and tile memory management is a non-trivial problem and has to be addressed in future work. Also, we would like to optimize the trade-off between schedulability and the widening of the local link. Thank you very much for your attention.